Okay, YouTube, in this video we're going to continue exploring how to find zeros of very complex polynomial expressions, but what we want to do is we want to bring up a very important fact about complex zeros, and that's that they come in pairs. That is to say that if f of x is a polynomial function that has real coefficients, okay, then we say if a plus bi is a zero, then the conjugate a minus bi must also be a zero. And basically this consequence always kind of tells us that if we know one zero is a plus bi, then the other one must be a minus bi. And that consequence follows the fact that, well, we probably used the quadratic formula to find this in the first place. And recall that the quadratic formula is something that says, well, your two answers here are going to be conjugates regardless because of that plus or minus that exists in their nature. So that being said, let's go ahead and take a look at what we have here, and we'll explore how we can use this to our benefit here. So it says find all the zeros of f. Given that, I'll go ahead and tell you that this is a zero of the function, okay? So now, the fact that we know that x equals 1 plus 3i is a zero of this function, because of our linear factorization theorem, basically means that, well, if that is a zero, then x minus 1 plus 3i, that must be a factor of the original polynomial. And the reason why this is so beneficial is because, well, what we can do is we could say, well, if this is a zero, okay, 1 plus 3i, also that 1 minus 3i has to be a zero. So now we have this other linear factor that is x minus 1 minus 3i. And what we're going to do here is we're actually going to recompose these and find something that we can long divide out of this polynomial. So it's a little bit longer problem here, but we've got this. So first things first, what I want everybody to do is when we set up these two linear factors, x minus this 1 plus 3i and x minus its conjugate 1 minus 3i, what we're going to do is reassociate things. This means that this negative in front of parentheses in each of these here we're going to distribute, and so we would get x minus 1 minus 3i, and then over here we'll get x minus 1 plus 3i. And we'll just reassociate these so that we recognize that really what we have here is a difference of squares. We have this minus this, this plus this, these conjugate pairs. So what do we know about a difference of two squares, or at least multiplying conjugates? We know that it multiplies out into a difference of squares here. So we'll get x minus 1 times x minus 1, this first entry here, and then we'll get 3i times 3i in the back. So now simplifying this, we are going to need to take x minus 1 times itself. And then this negative 3i squared, so minus 3i squared is going to be 9i squared when we use our power of a product property here. And remember that I squared, really that's just a negative 1. So simplifying this further, foiling this first quantity out, these two binomials, we get x squared minus 2x plus 1. And this, it'll just become a positive 9. So our final expression here is x squared minus 2x plus 10. So essentially, I wanted to know this right here because I know that if this is a zero, then also that this is a zero, its conjugate pair. And if that's the case, then we could multiply their associated factors back together to get this polynomial that would give us these zeros in the first place. So because this polynomial here has zeros 1 plus 3i and 1 minus 3i, we can actually use that fact to say that, well, then it must divide into the original polynomial evenly. And so in this instance, we actually do need to use long division because our divisor is of second degree, or at least it's not a linear divisor here. So let's go ahead and put in our dividend. X to the fourth minus 3x to the third plus 6x squared plus 2x minus 60, and I'm going to move pretty quickly here. So we say, okay, x squared and x to the fourth, I can take that x squared times an x squared to get x to the fourth. So we get x to the fourth, x squared times negative 2x is negative 2x cubed, and x squared times our 10 here is 10 of these x squareds. Don't forget that we are subtracting off this entire quantity here. So distributing this negative throughout, we would end up with an expression that looks like this. We'd say that our x's to the fourth cancel. Looks like we have a negative x to the third power, and 6 minus 10 is a negative 4 of these x squared things. We'll carry down and we'll start up again. So we'd say, okay, so now what can I take x squared times to get this negative x cubed? And I would say that negative x would do the trick. So we would get negative x cubed when we multiply that negative x times x squared. Negative x times negative 2x is a positive 2x squared, and then negative x times a positive 10 is negative 10x. So again, we're going to subtract off this entire parenthetical quantity, which means we'll add the opposite instead. So subtraction, addition. So these cancel. Looks like we get negative 4 and negative 2 give us a negative 6 of these x squareds. And then 2 and 10 give us a 12 of these x's to the first, we'll carry down our 60 and we'll start up again. So now I'd say, what could I take times x squared to get negative 6x squared? It'd be a negative 6. And then negative 6 times x squared, well, we get negative 6x squared. Let me do this in purple here. Negative 6x squared. Negative 6 times this negative 2x is a positive 12x. I don't know if you see it yet, but negative 6 times this positive 10 is negative 60. We're about to subtract something from itself. And of course, this is no mystery. We knew that this was going to happen to leave a zero remainder because we knew that, hey, if these were zeros in the first place, then these were factors. And if those are factors, then that polynomial that gives us those factors that had those zeros is this right here. And we knew that this was a zero to begin with of this entire polynomial. So this must go into this one evenly. And furthermore, we would say that what you're seeing up here, that right there has the remaining 2 zeros in it. And I say 2 zeros because if we have a 4th degree thing, then we have to have 4 total zeros. So in order to kind of find the rest of the zeros here, what we'll do is we'll look at this top expression here and we'll ask, can we factor it? And I think I seem to see that we can factor this here. We would say that x squared minus x minus 6. If I set that equal to 0 to solve it, we get factors of negative 3 and positive 2. And so there are those right there. So looking at this, we would say if I set x minus 3 equal to 0, then we're going to get x equals 3, box it. And if I set x plus 2 equal to 0, we're going to get x equals negative 2, box it. So a grand total of how many zeros here? Well, we got 4 total zeros. We were guaranteed to get 4. And we said that they are negative 2 and positive 3 were our real ones. We were told that 1 plus 3i was a 0 right off the bat. And because 1 plus 3i is a complex 0, we know that 1 minus 3i, or its conjugate, has to be the other 0 because they occur in pairs.